Hi, welcome to this video. This video is about interesting proof of infinite primes, a simple proof with Taylor series. Okay, first we need a Taylor series for e power x. E power x is equal to x power 1 over 1 factorial plus x power 2 over 2 factorial plus x power 3 over 3 factorial plus etc. plus x power n over n factorial. N here is a random number, can be any number, and I just want to show you the formula. Plus it goes to infinity for any integer n. So this is Taylor series. Okay, then we need this one. If we want to find a greatest power of a prime p that divides m factorial, the formula, if we call that power p power alpha divides m factorial, and p power alpha be the greatest power of p that divides m factorial, the alpha will be achieved of this formula. This is m over p in the integer value of m power p, and this is the integer value of m over p power 2, and this is the integer value of m over p power 3, and it goes for all of the powers of p to infinity. And this is the definition of greatest power of p that divides m factorial. Now, I want to prove that the number of primes are infinite, and use it by contradiction. First, we suppose that the primes are finite, and so they are, for example, p1, p2, p3, and then pk. Okay, so all of the integers will be shown in this form. I can be any number. and alpha is integer, and p1 till p1, p2, p3 till pk all is the only primes which are finite. So, how I prove that primes are infinite? If I show you, okay, because I suppose that the all primes are finite, this e power p times p2 times p3 times till pk is an integer, so it can't be infinity. Yes, but I want to show you that these things here are infinity, goes to infinity. How? I want to show you how it happens. Okay, first I wrote it in this way: e power p1 times p2 times p3 times till pk is equal to p1 power 1 times p2 power 1 times till pk times power 1 over 1 factorial plus p1 power 2 times p2 power 2 times till pk power 2 over 2 factorial plus go on and go on plus n p1 power n times p2 power n times till pk power n on n factorial plus goes on in the same way. Okay, I want to show you that each one of these, I mean this one, and each one of these ones is greater than 1. I mean this one is greater than 1, this one is greater than 1, and this one is greater than 1. So if I show you this, we have infinitely numbers which every one of them is more than 1, so this will be infinity, and then this cannot be equal to this number, and that would be a contradiction. but I show you in this way. Here I've shown you each number is have the form of this. Because of that, n factorial will be shown this way, can be shown this way, and beta 1, beta 2 till beta k has this formula. But okay, we have this formula. This is P, okay. And we know that this is the integer value of this number. So this number is greater or equal to the integer of itself. It means we can write this and put here, but I suppose it's greater. I will say why it's greater, not equal. And this one integer value of this one, but this number I only wrote a number here, and I can have the greater sign here. So, but why the greater? Because after some point we only have zeros here. All the numbers will be zero. For example, n, for example, p1 n over the integer value of n over p1 power 1000 is 0. After that, all of the numbers are plus 2 zeros. But here we don't have 0. We have a very small number. So here we add a small number, and it goes up, but here nothing changed. So it holds here. And now we want to show you that this thing is less or equal to n. For this, we use this equation. If z be an integer and equal or more than 2, we have this equation. You can prove it by yourself. So if we replace p1 to z and multiply all to n, we will have n over p1 minus 1, p1 minus 1, and it is less than or equal to less or equal to n, because p1 is 2, 3, p1 is a prime, so p1 is more than 1, is an integer more than 1, so it can be 2 or 3 or 4 or 5, but so is prime, it can be 4. But if we think that is 4, it has no problem, because n over p1 minus 1 is less or equal than n. So beta 1 is less than n, so that beta 2, beta 3, beta 4 till beta k, the area of beta are less than n, not less equal, just less than n. So if we instead of n factorial use this one, p1 power this, p2 power this, pk power this, for instead of n factorial, we have a number, an integer, which is divided by p1 times p2 times p3 times till pk. But I just show it for a random number n. If I show you p1, p2, pk, p1, p2, pk, So if we write that, this will be transformed to this, and because n is more than b1 beta 1, this will be greater or equal to 1, this one 2, this one 2. So this is greater than 1. So I proved that for any number, for random number n, I proved that for random number n, for example, this random number n, this will be a number, integer, be an integer more than 1. So what happened? What happened when we have infinity 1? When we have infinity 1, it means this goes to infinity, but this was an integer, so this is contradiction.